Hi, welcome to Exponential Functions, Differentiation. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. This calculus lecture comes from Larson's 11th edition calculus text, chapter 5. Specifically, section 5.4, exponential functions, in which we talk about differentiation and integration, but I've cut this into two parts. I don't like my videos to get too long, so part 1 is just the differentiation, and in the next video I'll talk about integration. Keep in mind, if you need a refresher on the algebra involved with exponential functions, please do so in whatever way you want. Mine is not the only resource. I also recommend Khan Academy and several others. You can find those on my webpage at UTEP. Just Google my name and UTEP and it'll come up. So, derivatives of natural exponential function. Let u be a differentiable function of x. This is why mathematicians and scientists love a base of e for exponential functions. The derivative of e to the x is itself e to the x. The derivative of e to the u is e to the u times the derivative of u. We might write that as u prime times e to the u, which says the derivative of the exponent multiplied by the original function, the e to the u that we started with. So anytime we take a derivative of e to some power, we're going to have a copy of that original in our derivative. So if I want to find the derivative of y equals e to the negative 5x, the derivative is negative 5, derivative of the exponent, multiplied by a copy of the original, e to the negative 5x. If y equals e to the negative x squared, my derivative will be derivative of the exponent times the original function. So negative 2x e to the negative x squared. If we have y equals x times e to the x, we have a product rule, right? X times e to the x, so first and second. The derivative is first derivative of the second plus second derivative of the first, product rule. And I could simplify this just by taking out that multiplication by 1. If you wanted to, you could factor out the e to the x times parentheses x plus 1, close your parentheses. But it's not entirely necessary. This is a good answer. If we have y equals natural log of e to the x, don't just jump in and start using rules. Keep in mind that the natural log and e are inverse functions of each other. So the natural log of e to the x is just x. So if y equals natural log of e to the x, then the derivative is 1. That's it. Do not make this harder than it needs to be. We've finally reached a point in the semester where it's about time we get a little bit easier material. Find the derivative. Y equals x to the x, e to the negative x. Now, check that out. X to the x. I have no idea. Is this a power function? Is this an exponential function? What do I do? And if I don't know, I'm going to use logarithmic differentiation and just tear it apart. So we take the natural log of both sides. And when we take the natural log of the right side, we'll use exponential properties. Now let's use logarithmic properties. This says the log of a product is the sum of the logs. So the natural log of x to the x can be simplified as x natural log of x, also using a power rule. The natural log of e to the negative x, well, remember the natural log and e are inverse functions, so that is just negative x. But now it's easy. Natural log of y has derivative 1 over y dy dx equals, I'll use the product rule. X is first, natural log is second. I have first times the derivative of the second plus second times the derivative of the first, but the derivative of x is just 1, so I didn't write it, minus the derivative of x, again, just 1. And I'll multiply both sides by y in order to simplify. What do I have here? This x times 1 over x, that's a 1. That's minus 1. So in this line, this is just the natural log of x. Multiply on both sides by y, and I'll have the natural log of x times x to the x, e to the negative x. It's a goofy looking one, but using logarithmic differentiation, something we can easily handle. If y equals e to the x minus e to the negative x over 2, I could think of that over 2 as a 1/2. Then the derivative of e to the x is itself. Subtract The derivative of e to the negative x is negative 1, e to the negative x. This gives us an addition. When we simplify it, we can put our 1/2 back in, and we get e to the x plus e to the negative x all over 2. And you'll find later in calculus that these are pretty interesting functions. You'll be not only surprised, but hopefully pleased when you find a little bit of mathematical symmetry going on in our later lectures. Alright, enough of that math for beauty's sake. What are we going to do with it? Find the equation of the tangent line to the graph of the function at the given point. If y is e to the negative 2x plus x squared at the point 2, 1, the equation of the tangent line requires us to have a slope. We know the slope means we have to find the derivative. So the derivative of this function is the derivative of the exponent minus 2 plus 2 to the x, not 2 to the x, negative 2 plus 2x times the original function. I know my slope of the tangent line is the derivative evaluated at 2. So when I put in 2, I'll have negative 2 plus 4. In my exponent of e, I'll have negative 4 plus 4. Negative 4 plus 4 is 0. E to the 0 is 1. 1 times 2 is 2. So my slope is 2. The equation of the tangent line is y minus 1 equals m, my slope at 2, times x minus 2. Distribute the 2, add 1 to both sides, and I have the equation of a tangent line. Remember, you can always graph the original function and the equation of the tangent line together. Make sure not only that it hits here at 2, 1, but that it doesn't hit anywhere else near the function. Right, it might hit down the line a little bit, but in the area around 2, 1, this should be the only line that touches. This should be the only time this touches our function. Find the equation of the tangent line to the graph of y equals e cubed, natural log of x, at the point 1, 0. Well, e cubed, that's just a number. We might not like it. It's not a nice number like 4. But e to the third power, that's just a constant. So the derivative of y equals e cubed times the natural log of x is e cubed times 1 over x. Just a constant. If it were a 4, we just leave the 4 out there. Same thing for e cubed. Now my slope for the tangent line is given by the derivative evaluated at 1, which 1 over 1 gives me 1. So I'll have e cubed times 1, which is e cubed. Hideous? Yes, but we can find the equation of the tangent line. Y minus 0 equals a slope of e cubed times x minus 1. Distribute my e cubed. Y equals e to the third times x minus e cubed. Implicit differentiation using exponential functions. E to the xy plus x squared minus y squared equals 10. I want to find dy dx. So in my first step, I find the derivative of e to the xy. Notice the product in the exponent. So the derivative of the exponent is x dy dx plus y times 1 multiplied by the original function. The derivative of x squared is 2x minus the derivative of y squared is 2y dy dx. And on the right hand side, the derivative of 10 is 0. We'll distribute x dy dx times e to the xy, y times e to the xy. We have our 2x and our minus 2y dy dx equals 0. Things that do not involve dy dx are subtracted to the other side of the equal sign. Anything that does have a dy dx, I've factored out the dy dx so that I can divide and solve. Dy dx is a negative. Right? They're both negative, so I factored it out. 2x plus y e to the xy over x e to the xy minus 2y. So whatever has the dy dx as a coefficient along the way is going to end up in our denominator. What doesn't have a dy dx ends up in our numerator, as long as we move it to the other side of the equal sign first. What about second derivatives? Yeah, we could keep going with this all day. I'm going to use a highlighter on this one, though. It's kind of crazy how this builds on itself. So if g of x is the square root of x plus e to the x times the natural log of x, our first derivative is, alright, The derivative of the square root is 1/2 x to the negative 1/2 plus e to the x times the natural log of x. We'll use a product rule. E to the x is first, natural log is second. So this is first times the derivative of the second plus the second times the derivative of the first. Remember, e to the x is its own derivative. I'm going to simplify that a little bit. I'm going to keep in mind that I'm going to find the second derivative, so I'm not worried about positive exponents or anything. E to the x times 1 over x becomes e to the x over x. And notice, e to the x times the natural log of x, we have a copy of the original in the derivative. So that's our first one. A copy of the original shows up in our derivative. All right. Now, the second derivative. Bring down the negative 1/2. I'll have negative 1/4 x to the negative 3/2, right? Derivatives, we subtract 1. I'll use the quotient rule on e to the x over x, so that's low, d high, minus high, d low, the derivative of low is 1, over low squared, plus the derivative of e to the x natural log of x, we already found that. The derivative of e to the x times the natural log of x is right here. So that is also right there. It just keeps repeating itself over and over again. I can simplify my negative 1/4 x to the negative 3/2. Separating my fraction here, x e to the x over x squared simplifies to 2 e to the x over x. You can see a copy of the e to the x over x does appear. Minus e to the x over x squared. And we already know that this e to the x over x, that's where our second one came from, plus e to the x natural log of x, once again, another copy of the original from both the derivative and the original function lands in our second derivative. So when you're using e to the x, taking the derivative, you're going to see it repeatedly. You're going to see copies of it in first, second, third, as many derivatives as you want to take. That's it for the natural exponential function and differentiation. Second part, part 2, talks about integration. Thanks for listening.